All right, thank you very much, Alexei, for the kind introduction, and thanks for having me here. So it's really great to see such a lively young community here, and and such an active one of the world centers here for quantum science forming here at JQI, and I'm really excited to see all the progress that's been happening here. And the last time I was here, the building didn't exist, the new building didn't exist, and we were just talking about it, already getting excited about the new building, and now, this morning Ian already gave me a tour through the new labs and all the exciting things that are happening. So I want to tell you a little bit about some of our recent work, and in a sense, the colloquium should have been before this talk, but okay, that's how it is. So we're going to go through a little bit more specialized things, advanced things, and tomorrow will be a little bit more fundamental things. So I've picked kind of three subjects I'd like to talk about from three of our teams. One is many-body localization. Of course, a topic that's of interest to many, many people here too. Chris, Shankar, many others, and I'll talk about our recent experiments and our questions that we hope to be able to answer over the next year or so. Then I'd like to turn to topology and tell you about the Thouless Quantum Pump, and finally tell you a little bit about our Rydberg quantum gas experiment. So, okay, let's see if we make it through everything. We don't have to, so I think you just should interrupt me if you don't understand something, something's unclear. Just interrupt me whenever you feel that something is unclear. Okay, so let me get started. The first topic on many-body localization. This has been joint work together with Ehud Altmann's group, Ronen Fosk and Mark Fisher. And so we have 2 publications out on this, but many experiments ongoing, and I'll tell you a little bit what we're doing in this direction. So the question we're trying to answer is actually a very fundamental question and goes back to the question, what happens in the process of thermalization? How does temperature arise in an isolated system? So let's say, for example, you have this cup of coffee with coffee here and milk here, segregated from each other initially. And, of course, they will mix over time. There will be thermal equilibrium forming in the system. And a little bit for an isolated quantum system, typically it's the same thing that happens. So you start out with some highly non-equilibrium state, which is not a thermal state. It's an isolated system. It's not connected to the environment. And then because of the interactions between all those particles, this initial state, the information about the initial state, will be lost over time, just as this is lost over time here as this system mixes. And typically then we can resort to a classical hydrodynamic description of these remaining slow modes that describe the dynamics of our quantum system. And this is typically what happens, and typically then locally temperature arises in the system. I'll specify that a little bit more precisely in a second. Now, the topic I want to talk about, many-body localization, has captured the interest of so many people because it actually is a dramatic departure from this paradigm which we usually encounter in nature, where we can have basically local quantum information set up initially in the system, then let it evolve, and in principle, from a theorist's point of view, it will stay there infinitely long. There will be memory of that initial state for infinitely long times, and there will be no kind of thermal equilibrium arising in the system. And so in a sense, it's also kind of on a many-body level, this elusive interface between the quantum and classical world that has driven so much work in quantum optics. Same question asked, but now for many-body systems. When do systems start to behave classical, and when can we describe them by classical ways? All right, so 2 good reviews I really like. I can highly recommend to you on the topic if you want to get interested in this and learn a bit more. It's one by David Hughes, Rahul Nankishore, and Vladimir Oganessian, and Ronen Fosk and Ehud Altmann, both in this annual review of condensed matter physics issue. Okay, so let me talk a little bit more about what I mean by thermalization. And connected to that is this so-called Eigenstate thermalization hypothesis on the level of eigenstates of a many-body system. So let's say we have an isolated many-body system, this big box here, and we're in some eigenstate of that many-body system. That can be a very highly excited state of that many-body system. And what we mean by this, what this eigenstate thermalization hypothesis assumes, there's no strict proof of that, but that's what we find typically for most systems, that if you trace out the remainder of the system and just leave kind of a small system, subsystem A here, then this reduced density matrix of this reduced system will look like kind of a thermal system. So it will look like a thermal density matrix, and this is what we typically find for most kind of quantum many-body systems out there. And the entropy of that kind of system here, the subsystem, it grows like the volume of that system. So we say the system has volume law entanglement described by the system. So that's something characteristic for kind of this thermal state, for this Eigenstate thermalization hypothesis that people have put forth here, Deutsch, Srednicki, Rigold, Dundko, and Olshani. And
more extreme, right? A could be just a single eigenstate.
Yeah, that could be a single eigenstate. It's in a sense, it's an extreme level of equivalence of ensembles where the micro,
just small.
right?
One eigenstate
one eigenstate is
is enough.
enough. So that's taken kind of the equivalence ensemble to an extreme level where the microcanonical ensemble described by one eigenstate, one many-body eigenstate, becomes equivalent for local observables to kind of a thermal description. Yeah, so, but again, there's no strict proof of this. We'd have no proof of this, but that's typically what we find. And what I want to show you actually that one way of thinking about many-body localization, again, is a dramatic departure from this kind of description where this actually completely fails. Where again, the system does not act as its own heat bath. It cannot produce kind of these thermal states for local observables in the system. And so it's really a striking departure from this kind of paradigm. So in terms of theory, there's been tons of theory on this. I mean, you go on the internet and you look on the papers, there are literally hundreds of papers on this. So this is something, of course, this is not a new topic, actually. This is, of course, what motivated Phil Anderson when he looked at interacting disordered system, to find out whether you can have insulating states for interacting disordered system. So by that time, he wasn't able to answer the question for interacting particles, but he was for non-interacting particles. That's what we call Anderson localization today. But still, this question, of course, has driven a lot of people, in condensed matter physics for decades. And there's huge literature now on this. There's just, I mean, I would say from an experimental point of view, there was been kind of a big problem. There's basically no experiments when we entered the field. And now, with Chris's and our experiment, there are two experiments. Okay, so I would say there's a lot of room for experimentalists to carry out experiments in this direction. And I think, as I hope to show in the end of that part of the talk, there are actually so many open questions, so many things we don't understand. It's really an exciting field of research to do.
May I ask you something?
Yes.
Because I don't think you'll touch upon it. People who work in solid-state glasses, like quantum glass, electron glass, and
yes.
so on, they believe there's some connection. Whenever you write a paper, I get emails from them.
Yes.
And I am a bit confused. I'm trying to understand it. Do you have a view on that?
Well, I think at this point, I think there's no clear view. I'll touch upon this actually when we couple, because I think eventually when you couple theoretical MBL systems, which can only exist in a completely isolated environment, so they can never exist in reality,
that's my response also, right?
That they will look a little bit like also glasses. So we can come to that interesting question maybe at the end. Yeah. All right, so let me try to touch upon a little bit how we measure localization in the cold atom world. And one kind of very successful way of doing this was kind of put forth by the groups of Massimo Inguscio and Alain Aspect in Lens and in Paris, measuring Anderson localization. And the way they did that was to start out with a kind of initial state where particles are localized, non-interacting BEC, and you let them spread out in the trap in the presence of disorder, and then you look and see that the wave function gets stuck over time, and you can really see these beautiful exponential tails and measure this localization length, this Anderson localization length in that problem. And the recipe for kind of measuring many-body localization, the lack of thermalization, will be kind of very similar. We're going to set up a highly non-equilibrium initial state. We're trying to see in the long run, does the system remain information about this initial state, or is this information completely washed out, and do I approach a thermal equilibrium state in the system? I should say there's also beautiful work from Brian DeMarco's group on this, who looked at global mass transport of interacting fermions in these kind of trapping potentials. That should also be mentioned in that context. Okay, so here's the system we set up. So this is kind of a two-component fermion system with tunable interactions. So we have a potassium-40 mixture of two spin states where we have this beautiful Feshbach resonance, which allows us to tune the interactions between the particles at the knob of this magnetic field here. We're setting up quasi-random disorder by adding a kind of incommensurate lattice potential, second lattice to our original lattice. And this realizes the celebrated Aubry-André model without interactions. So you see, if you look kind of on this looks pretty disordered to you, but in reality, it's superimposed this incommensurate kind of lattice potential on top of the original lattice potential, and then you just have tunneling of those fermions in the lattice. So we know a couple of things, of course, about the Aubry-André case that has been long researched, the non-interacting problem. We know, for example, when the ratio of a disorder to kinetic energy is smaller than 2, then all eigenstates are extended. When delta over J is larger than 2, then all eigenstates are localized. So Anderson localized in the problem. So now what do we do in the interacting system? So I'm not going to tell you how we do this in practice, but suffice to say what we can set up in the experiment, the initial state is what we call this charge density wave, where we have only even sites populated in the lattice. So obviously that's not a thermal equilibrium state. That's not the ground state or any thermal equilibrium state of the system. So it's a very, very kind of strange initial state. And what we're going to do then, in the presence of disorder and in the presence of interaction, just look how does this state evolve? And if we then read out this charge density wave at a later point in time and find there's kind of residual information about the initial state, then we can say that there's a lack of thermalization, there's kind of many-body localization in the system. So that's our kind of naive way of identifying the many-body localization transition. And the parameter to quantify this is this so-called imbalance, which just characterizes the even-odd population difference on even-odd sites that you can see here. So it's kind of a visibility, like in optics, a visibility of this density wave that you're setting up. Now, there are a couple of things we know about the problem. Let me go through them. So if you have non-interacting particles, we're back to the Anderson localization case. For Anderson localization, we know for delta over J smaller than 2, we have these extended states. And delta over J larger than 2, everything is localized. Okay, that's one reference point. If I have initially no doubly occupied lattice sites here, the very strongly interacting fermion problem for U going to infinity actually maps back to the non-interacting fermion problem. So we also know that this point here, if I have no initial number of doublons, also is exactly the same as this point here. So this one here has to be exactly the same here. Now you can argue what happens, qualitatively. Usually when you add interactions, you tend to delocalize the system a bit more, so you need stronger disorder to localize it. So is it mine? Is it mine?
No.
It's not mine. No? Is it mine? No, I don't think it's a cell phone. Let's see. No, not yet.
Even goes with the speakers. I didn't know.
Okay, I think it's fine. All right. So we have the. No. Is it this one? No, it's not. Cannot be this one. Can't be. But it sounds awfully like it's this one. No. You can turn it off and see. Yeah, I was. Turn it on again. So I think it's gone now. Okay. All right. Maybe it was some JQI ghost in the system. All right. So we know these reference points, and we also kind of know that typically when we add interactions, we tend to delocalize the system a bit. But if this has to be the same as this point, then there's no other way than this phase diagram to look something like this on just qualitative grounds. Okay, that's our first guess of what the phase diagram should look like for this many-body localization transition as a function of interaction strength in my system. All right. So here's the experimental setup. So here's what we're going to look at. We have these 1D tubes. We create an array of one-dimensional systems. We add this quasi-random disorder along the direction of the tubes. We set up this initial charge density wave. And what's really important here, this, to the best of our knowledge, is kind of isolated from any thermal reservoirs. Okay? So that's what makes it really different from a typical condensed matter experiment where you're always connected to a thermal reservoir in your cryostat. And that will not allow you to do experiments like this because you're always going to thermalize to the temperature of the cryostat, right? Here, that's not the case, but we'll come to an interesting question in the end. Of course, when I say this is not coupled to the outside world, this is, of course, an approximation. Yeah? We are coupled to the outside world through spontaneous emission, for example. We're coupling to photon bath. We might be coupling to between these tubes. I'll come to that question. So when I say we're not coupling, it's really an theoretical idealization of the problem. But to the best I think we have in the labs, this is pretty decoupled from the environment. So it's the setting we want to study. So here's what happens. You look at this imbalance as a function of time, and you do this for different disorder strengths and interaction strengths.
Immanuel, I have a question.
Yes.
Imbalance, so you're averaging over it because it It's NE minus NO.
NE minus NO.
So it's the overall.
Overall,
NEs,
not spatially resolved.
okay, not spatially.
Not
resolved.
spatially resolved.
Okay.
And now what I'm going to show you, when I show these time traces, this is also disorder averaged.
Okay.
Okay, so this is the evolution of the imbalance, disorder averaged, not spatially resolved. Actually, we could learn a lot if we could spatially resolve, but yeah, that's a
Now,
separate.
what do you mean by disorder averaged?
So you do the same, so you let the system evolve, you read out the even-odd, average even-odd fraction, and then you repeat the experiment for a different phase of the disorder, okay? And then what I'm showing here is the disorder averaged of that, okay?
You disorder average each NE and NO, or you disorder average
No,
the
no,
whole thing?
no, first you carry out the experiment, you read out the average imbalance that you have for that system, and then you repeat the experiment for a different disorder and you average that, okay?
But you don't average the final quantity, you average just individual NE and NO, right?
You first calculate the imbalance for a given disorder, and then you average over the imbalance for different disorders.
Average the final
Yeah,
quantity.
yeah. And this is what you see, and already that picture shows you that there's a lack of thermalization in the system for disorder. So why? Let me show you the case without disorder. So without disorder, it just happens what you would intuitively expect. The system starts with this density wave, but now as it starts to spread out, it just spreads out evenly over the even and odd sides. So there's nothing that prefers even over odd sides, so the imbalance goes to zero, obviously. Now for a thermal state, it always has to go to zero, even in the presence of disorder. If you have a thermal state, there's nothing in a thermal state that prefers even from odd sides. Okay, so the odd and even side occupation has to be the same if you're in a thermal state. So if you see, for example, like here, that you are not approaching this kind of zero value, you're kind of approaching this steady state value here, this constant value here, then you can say you have a lack of thermalization of the system. The system maintains the information about its original state, and there's lack of thermalization in the system. All right, so now just to make a few consistency checks that we understand our system well, here's what happens for the non-interacting case. When we tune with the Feshbach resonance to u equals 0, we measure the imbalance as a function of the disorder strength, and if we would have no trap, you would see this nice kink at delta over J2, which signifies this Aubry-Andre transition from the delocalized to the localized phase. When with the trap, you see it's a little bit smeared out, and just from exact diagonalization, we can see that our data points, which are the blue points, fall very nicely on that curve. So we understand the non-interacting case as a reference case. Yes? Yes? That's the tunneling time. So everything here is in units of the tunneling time, so h bar over j. Okay, so this tau, sorry, missed that. So this tells you this is evolved up to like 30 tunneling times. I'll show you later time traces up to several hundred tunneling times quantum evolution. Okay, so we understand the non-interacting problem. That basically exactly follows what we expect. And now we can compare what happens if we have interactions in the system. So the line that I showed you, let me walk you through this 2D plot here, was the non-interacting line that cut through this graph here. So this was the non-interacting line I showed you. The imbalance is now encoded in color. This was non-interacting. You see it up to kind of 2, it basically is delocalized and then starts to rise because of this transition to this Aubry-Andre localized phase. Now, as you see, when you add interactions, you see this nice kind of W shape forming. So interactions indeed tend to delocalize the system, but at some kind of critical disorder strength, again, it completely localizes, and we find a finite imbalance in the system again. So you see this again if you make these plots here as a function of u over j, imbalance for different disorder strengths, you see this characteristic W shape. So this W shape is also interesting. That's a feature of the Hubbard model, that you have a nice dynamical symmetry between u and minus u. If your initial state fulfills some special conditions, we know from earlier experiments it has to be like that. So it has to be the symmetry between u and minus u in the system. So they're exactly the same. Now, if we compare this to theory, and this is what Ehud and his colleagues did in Israel at the Weizmann Institute, they calculated this quantity that's famous entanglement entropy as a function of time. And here you see what happens for the system in the theoretical simulations. So initially, there's this initial ballistic spreading of the particles. So the particles, you set up this charge density wave, particles start to tunnel. They spread ballistically because there's no other particle there. And then they start to kind of see these interacting particles, and then you see this characteristic log T entanglement entropy growth that is characteristic for an MBL localized phase after about 1 or 2 tunneling times. If you're in the non-interacting phase, you see you don't have this log T growth. This just stays constant. So you just have this initial spreading and then kind of the entanglement entropy stays constant when the particles have spread out over a length scale corresponding to the Anderson localization length. Now what's interesting is that what people had found out that the slope of this entanglement entropy growth, that is related to the famous many-body localization length, although I'm not so sure people understand exactly what it means, actually, this many-body localization length. We can talk about that too. But if we take that slope as one measure for a length scale, characterizing the length scale over which kind of particles are localized in whatever space, then one interesting feature, we see that this maximum, there's a maximum in the entanglement entropy slope here around U over J5. So when you just take the slope of these log t curves, there's a maximum, and this maximum exactly falls where we see a minimum in the imbalance. Okay, so this is the imbalance we can calculate and we can measure. And this minimum of the imbalance is, of course, something that you would expect to be minimal when the localization length is largest. Okay, when the particles spread out the most, the imbalance should be at its smallest value, and we indeed see that these two correlate very well with each other according to our expectations. Now let me come to the point that I pointed out initially. If we have no doublons in the system initially, no doubly occupied sites initially, then the zero interacting point should give exactly the same as the infinite interacting point. And we indeed see that. So if you look at the steady state imbalance after a long time evolution, as a function of interaction strength, you see that the non-interacting case is exactly the same as the infinitely interacting case. So we indeed recover this behavior that we know from strict theoretical mapping grounds has to be like that, we recover. Of course, when you add doublons, if you start with a state which has initially a lot of doubly occupied sites, then this mapping does not hold anymore, and you see there's no symmetry anymore between u equals 0 and large interactions, positive or negative in the system. And we can understand that, of course, also very nicely, I think, intuitively, because now these doublons, if you think those doublons as new quasi-particles with a kinetic energy j squared over u, now, if u is very large, then this kinetic energy of the doublons is very small, and compared to the disorder, this gives an even smaller ratio than the single particle kinetic energy over a disorder. So they kind of feel the disorder, upshot, the doublons feel the disorder even stronger than the singly occupied particles, and kind of are more localized, and therefore we see a higher steady state imbalance value in the system. All right. Let me now add one interesting twist to this. This was something we put up recently on the archive, and it comes actually back to one of your questions, changing dimensionality. If we now take these 1D tubes, as we've set them up here, and now we ask what happens if we start to couple these tubes. Okay, so they're not isolated 1D systems, but they're coupled in the orthogonal direction, and we have no disorder in the orthogonal direction in the problem. If you have no interactions, the problem is separable, strictly separable, and actually you should obtain exactly the same result. And that's what we see. So this is 1D, 2D, 3D, no interactions in the system. We set up this initial charge density wave, and you see this nice Aubrey-Andre transition, and there's actually absolutely no difference between the 1D, 2D, or 3D case, okay, in the non-interacting problem for the Anderson localization. If you, however, have interactions in the system, there's kind of a dramatic difference. So here's the imbalance as a function of tunneling time, and now I'm plotting over up to thousands of tunneling times in the system, okay? And you see that actually there's a dramatic difference. So if you're in the 2D case, you never ever approach kind of a steady state regime. You always immediately decay here in the imbalance. There's no plateau approach. And for the 1D regime, we see that for long time scales, for hundreds of tunneling times, we start to depart from this kind of steady state value. There is some residual decay, and I'll come back why that happens actually in the system. So here you can also see that striking behavior. If I plot this steady state imbalance as a function of interaction strength for the 1D or 2D case, you see the 1D has a very high imbalance. If you only add a little bit of interactions in the 2D case, you immediately decay. The imbalance almost decays to 0. Now, one explanation for that is if we go to this setup, if we have these tubes now in the orthogonal direction, they can act as a heat bath that thermalizes the tubes in the orthogonal direction. So these kind of tubes that we have in this direction, the vertical direction, can act as heat baths that basically kill MBL immediately, and that's what we see in the experiment. So there's no of this plateau is visible in the experiment.
But it's strange, right? Because those heat baths are localized systems.
No, they're not. There's no disorder in that direction.
Oh, there's no disorder.
No disorder in that direction. There's no
Y direction, lack of disorder.
Y direction, no disorder. Only X direction disorder. That experiment should be still done. It's actually an interesting experiment. I'll come to that. But with 2D disorder, looking at that, that's a very interesting experiment.
But each of those other 1D systems that you're coupling
Right,
is
unlocalized.
itself separately disordered.
No, they have the same disorders.
Yeah, they have the
So
same
okay.
it's
So let me.
like
So these guys, they
Yeah.
have the same disorder.
Does that matter, the fact that it's the same disorder?
I think it matters because otherwise the problem would not be separable anymore.
No, but it's a bit
So
counterintuitive. So let's say those are baths. I mean, your experiment doesn't have a full theoretical explanation right now.
Yes.
But let's say those are baths. One would not usually expect that I couple to a localized bath and the system immediately becomes ergodic. Because that's a localized bath, this is a localized system. How is it becoming ergodic? So there is something interesting here. It's not just the Y disorder. If you think of each X chain when they're independent as localized systems, they're all non-ergodic. You are coupling two non-ergodic systems, and your system is becoming ergodic.
okay, let's talk about that. I mean, okay, I would say it's not really fully understood exactly, but I think it should make a difference. I think there should be a difference, at least from the problem of being separable. Certainly what we have, in this experiment, what is definitely important, there's no disorder in the Y direction. So the outcome could be completely different if there would be disorder in the Y direction. But nobody has ever seen MBL for 2D systems. I mean, the arguments that have been put forth by Altschuler, Alaina, and company, in principle, should hold also in higher dimensions. But numerically, there's absolutely nothing. We know nothing whether it exists in 2D. And there's anyway, also in 1D, there's only one strict mathematical proof by Imbree's group on a special spin model. So we know strictly not very little things are strictly known. So certainly an experiment, absolutely an experiment to be done. And the outcome would be quite different if there would be disorder in the Y
As you
direction.
of course know, the theoretical argument is it is an infinite dimensional localization.
Yeah.
It's on the Hilbert space.
Yes.
So changing spatial dimension should not matter. I don't buy that argument, but
Yeah.
this is a theoretical
Okay.
argument.
I'm an experimentalist. I want to do the experiment,
This is
and
a theoretical argument.
we will see. We will see.
But it seems to me that coupling to a large number of additional
sure.
non-ergodic systems, not unreasonable, that becomes ergodic.
Sure. Yeah. I totally agree with that. I mean, if you couple to something which has more degrees of freedom, then it should. And then it's also a question, what is the bandwidth of your bath, essentially, you're coupling to? So that's another interesting question. How strong is this coupling between this system and the orthogonal system? So we see that there's this striking difference between the 2D and the 1D system, also shown here in the imbalance. Also, if I look at the lifetimes of the 1D kind of MBL system and the 2D case, you see it's much shorter in the 2D system as a function of interaction strength, all supporting the argument that interactions destroy many-body localization in this 2D scenario very rapidly. And I think it also tells us right now, if you've been asking me what limits us, coming back to our original data, what limits us, how long can we see this plateau? I mean, okay, ideal MBL would tell you see that to infinite times. That's what MBL tells you. For an isolated system, if you're in a true many-body localized phase, you should see at infinite times that the system maintains information about its initial state. Now we know, as I tried to explain, no experiment will ever be able to test that because all experiments are coupled to the environment at some point. We understand that this residual decay now here is entirely due to the fact that we have a residual tunnel coupling between the tubes. So even for our highest lattice depths, let me go to the picture again, Even for our highest lattice depths, the transverse coupling between the tubes is not low enough to make them exactly 1D.
What was your highest lattice depth?
Yeah, that was about 35, 40 recoil. It's pretty low, pretty high lattice depth, pretty low coupling. But if you look at this curve here, this lifetime curve, as a function of the transverse coupling to longitudinal coupling, you see there's no plateauing that we can see. So we can still say that for now, we are just limited by the residual transverse coupling in how long we can see this kind of MBL plateau arising in the system. And that's an important information. All right, let me turn to a completely different experiment on a different setup that tries to access this problem and ask the question of the 2D. Yeah, Victor.
So I have
yes.
a question.
Yes.
Is it possible to put bosons in there and see what the difference between fermions and bosons?
You're worried that you're starting with an integrable model, or?
So,
You
for
are-
bosons, you're not supposed to see this, right, basically?
No, for bosons, I think you would see. My feeling is you would see exactly the same thing. My understanding is you would see the same thing. The only criticism you could raise with fermions, if there's no disorder, you start, of course, with an integrable model. And we know that there's also integrable problems can also show lack of thermalization, but that's not what we want to show here. We want to show Many-body localization is a much more generic phenomena. And if you start with a boson problem, you start with a non-integral problem. But I think my feeling is we didn't do it. This experiment will be with bosons, what I'm going to talk about now. So this will be with bosons. But my feeling is it would do exactly the same thing. Okay? All right, so let me tell you about this other experiment. And this now tries to look at this dynamics and tries to access a little bit what is this ominous many-body localization length in the problem that we're trying to find in a different way. And now what we're doing is we're looking at a true 2D system. We're looking at bosons. We don't have tunable interactions, unfortunately. There's no Feshbach resonance for rubidium, but we have an interacting system. With the lattice, we can change the interaction parameters in the system. And what we're going to do, we're going to be able to project disorder, true 2D disorder, so it's not quasi-random disorder, onto the atoms, okay? And now what we're going to do is we're going to prepare a very special state. So if you're going to come to the talk tomorrow, you'll see we can make these nice mod insulating states. We can see them with a microscope. And what we do with this mod insulating states of unity filling, we just cut them in half. We just make a very sharp domain wall boundary in the system, okay? So this is what the initial state looks like. This is a photo of the quantum gas initially. And initially, it would have spread out like a circle, and we just cut away half of it. So we made a very sharp interface. And then what we're going to look at, we're going to look how does this domain wall spread into the kind of disorder free space as a function of time. Does it fill out completely the system? Then it would be thermalizing. No, obviously, a thermal state would fill out the system completely. Or does it get stuck, the domain wall? And can we learn something from the length scale of this decay of this domain wall? And that's kind of a guess. It's not analyzed theoretically, but that's my guess that it will help us to understand what this many-body localization length scale is.
And during all this, there is an overall trap that is defining.
There's an overall trap. Yes. So you see what happens if you have no disorder, you can see here. So this is an initial picture, single realization, single snapshots, and when we average them over many realizations, you see that the system spreads out entirely over the entire trap and fills out the entire trap. If we have disorder in the system, now mind these values, there's some calibration factors, so this delta over J in absolute terms doesn't mean anything, but it means it's a disordered system, and you can somehow see that if you look even for long times, it doesn't seem to fill out entirely the trap. Okay, it seems to get stuck here at some side. And we can plot the variance of this domain wall. So just if you have initially a step function and then it kind of melts into this empty space with disorder, and we plot how that kind of spreads out, we see for the kind of for the system without disorder, we get this initial linear growth in time here of the variance pointing to a diffusive spreading of the system until it reaches the full system size. Whereas if we have disorder in the system, we see that it seems to kind of get stuck at this kind of finite variances. It doesn't explore the full size of the trap, and that already hints us that we are seeing also many-body localization in this 2D case.
So diffusion would be just a straight line?
Yeah, in this would just be the straight line here.
Levels of disorder you have,
Initially, yeah, we should take more data points here to confirm it here, but certainly we know that also for the non-disordered case, we know it should spread diffusively for interacting particles in 2D. Here's now the density, this steady state density plotted on a log scale. And we see two exponential decays, obviously. This one we think is due to the trap, and the initial one is the one that's interesting for us to MBL. So this is kind of this decay length that we get from this kind of sharp cut on. And we also check that this doesn't really change if you change system parameters. If you go to a weaker trap or a stronger trap, pretty much this length scale, so the slope here on this log scale stays the same. So we can extract a length scale of this decaying domain wall in the system and plot it as a function of the disorder strength. And I think here we see an interesting result that I would like to take with a little bit of caution because we really are trying hard to confirm this right now. So here's this decay length as a function of disorder strength. And for Anderson localization in 2D, it would diverge at 0 disorder strength. Okay? Here we're seeing a feature that diverges at a finite disorder strength, and we will be able to extract the critical exponents from this curve of this length scale, kind of this domain wall decay length scale in the system that points us to the fact that we're really seeing a phase transition here in 2 dimensions. Okay?
But is the non-interacting part true in your experiment? If you turn the interaction off, do you really see a decay at zero disorder?
Yes, so we
Is that
see,
correct?
yes. Well, so there's the problem of the trap, which is there, which makes things a little bit difficult in the non-interacting case. First of all, we did the non-interacting case, and it always stays in the regimes where this diverges, it stays down here, and seems to
So it's
diverge
very
much
different,
later.
But then the trap comes in, you have a cutoff.
Exactly.
That's
The trap,
you cannot go all the way to zero.
but you see the advantage with the non-interacting problem, also I can simulate on the computer very well, but we can check with the experiment, yeah? So what I think is exciting about this is that it points to the fact that indeed we can have MBL in 2D, and also we might have ways now of really getting to this many-body localization length, extracting this many-body localization length, and learning something about the phase transition, the nature of the phase transition here at finite critical disorder strength. Something you would also like to see, and that's ongoing experiments, if you come from this side here, you would like to see kind of a critical slowing down of the dynamics. Here we say we're in ergodic phase, thermalizing phase. Right? Here the system spreads out over the entire trap. But it might take very, very long to do so, okay? So, but there should be kind of a critical slowing down as you approach this from this side. So it would be good to bound this phase transition from both sides and really learn more about it.
That's a good idea, but that may be tricky. As you know, the hypothesis is that it's an infinite randomness phase transition. Z, the dynamical exponent, is infinity, in which case the slowing down is infinitely slow.
Yeah, sure. But I think any slowing down, any hints of slowing down on this side that point to the same kind of critical point here, I think would be nice in the system. Okay.
What's the difference between red and orange?
The two trap parameters that we chose. So this is the 40 Hertz trap and the 54 Hertz trap, just to make sure that what we're seeing is not kind of trap physics, okay, what we're extracting. And you see that they basically fall on top of each other. Okay, so I think many more checks have to be done. I think this would be a big result if it holds, but we have to really check this very carefully. Yes?
Would it be possible to do this in 3D to benchmark against like Anderson localization?
Yeah, 3D will be hard for us here because we don't have this microscope technology in 3D. We'd love to do it with fermions on our new fermion microscope experiment, which I'll tell about tomorrow. And there we could have these tunable interactions also. What I would really like to do, I would like to make this domain wall, keep everything the same, every lattice parameter the same, just turn the interaction knob, see if I have 0 interactions, it spreads out, I turn to interactions, it gets stuck. Okay, nothing changing in terms of lattice parameters. So really A-B comparison. So that's the experiment I would love to do, but it's not done yet. Yeah? Okay, so let me just put a couple of questions up, because there's so many questions out on this many-body localization transition. So we've started to look at coupling to the outside world. We've also started experiments where we intentionally induce kind of photon scattering and make use of the fact, try to learn how does the MBL system react when you couple it to a thermal bath. And maybe we can not only, because anyway it's going to happen in all experiments, but maybe we can also use this as a way to identify MBL systems because they react very differently from Anderson localized systems to coupling to a bath. Okay, so a new way of identifying this. There's the question of optical conductivity, local fluctuations we talked about. They are very interesting for identifying crucial features also in entanglement evolution, may be accessible with these quantum gas microscopes. I talked about the localization length. I really believe we don't really fully understand what it actually is, but people are telling me different things. So, but maybe, just suggesting as an experimentalist, let's try to use some things like these domain walls and see, can we relate them to kind of these more theoretical approaches of the localization length? Critical slowing down, entanglement, entropy growth might be measurable with the new techniques Marcus has been proposing in Harvard. So I think there are many, many exciting open questions out there. So I urge you, if you have an experiment which can contribute to this, I think it's an exciting time to get involved as an experimentalist in this. All right, and I should just acknowledge here the people who've been doing the work on the kind of first kind of experiment, the quasi-random disorder. This is Uli Schneider, he's now in Cambridge, and Hendrik and Pranjal are the key PhD students on this, and Michael. He just left us, and Sean is a postdoc. He's now back in Australia. So Hendrik and Pranjal have now taken over as key experimentalists on this disorder experiment. Okay, actually, make much slower progress than I thought, which is good. So I'll skip the Thouless pump, and I'll go to the Rydbergs, because I'll talk about topology a little bit tomorrow. And so switching completely gears, I want to talk about our experiments on Rydberg atoms in lattices, and I think it's very closely related to ongoing work in Trey's group, Steve's group here at JQI. So let me remind you again with these Rydberg atoms why we're so interested in them. And so if we typically take our beloved rubidium atom and we excite it to the 43s state, the outer electron, the valence electron, the atom gets dramatically bigger. And for example, some things like the van der Waals interaction, they grow dramatically with the 11th power of this principal quantum number. So when you go to these highly excited Rydberg atoms, you have these highly polarizable objects that have dramatically strong interaction strengths in the system. And we want to make use of that, of these long-range interactions, and control them, engineer them, and see what we get. So here's what we do. This is done on our quantum gas microscope experiment. So we have a 2D kind of gas of atoms, well controlled in a plane. We excite, for example, with the 2-photon transition to this 43s state. And then we developed a new way how we can actually see these Rydberg atoms. So okay, let's say we make them. We make 3 Rydberg atoms. And in order to see them, what we do is the following. We basically remove the ground state atoms by shining a resonant laser transition on the 5s1/2 to 5p3/2, which just blows away by radiation pressure these ground state atoms. Okay? But the Rydbergs are not affected because they just stick where they were originally. They don't see that light. And then we stimulate the Rydberg atoms back down with this 2-photon process. So we shine in light at 480, and then there's just a spontaneous decay here at 780. So they just decay back, and they are then ground state atoms. And now we can image those, but we know those were the Rydberg atoms. Okay? So that's very nice, because now I not only can count how many Rydberg atoms I have, I also know where they were. I can see where these Rydberg atoms were actually in my quantum gas. And this is how it looks like. You take a thermal gas. So thermal ground state atoms are these red ones. We do this process at this Rydberg excitation, and then you find you had a couple of Rydberg atoms in there. And you see where they were with kind of micrometer resolution in the problem. Okay? All right, so now one thing we like to do is actually control the size of our initial state very well, because you know when you have long-range interacting physics, it's very hard because you have a single atom out here, you have long-range interactions, it might determine everything that's happening in the center of the system. Okay, so you really have to have very well control of what your initial state is. And to do that, we have these DMD masks that we just project light fields onto this mod insulator, and they allow us to cut out any shape of atom cloud you want. Okay, so we call this the cookie method. It's like Christmas is coming, right? It's like you make your cookies out of your dough. You just stamp them out. And that's exactly what we do, but now at a single atom level. And this just works very well. So just averages of how good our cookies are, how reproducible they are. You know, they're pretty nicely sized and shaped, have a hard boundary. So that's actually very nice in the control that we achieve over that. Now, when you excite to the Rydberg state, there's this famous effect, the so-called Rydberg blockade, where if you try to excite a single atom to the Rydberg state, you have the normal kind of Rydberg to ground state transition frequency. But if you try to excite a second atom to the Rydberg state, then there will be an energy cost you have to pay because of this very strong van der Waals interaction. And this is actually huge. This is really dramatic. If you, for example, look at this van der Waals coefficient for a Rydberg state in the 68s state, this is a 680 gigahertz energy shift per micrometer separation. So if you have 2 Rydberg atoms at 1 micrometer separation, there's an energy shift of the resonance frequency by 680 gigahertz. So these are scales that are totally unknown to cold atom physicists. Okay, so they are beyond anything we have ever heard about. So it's a really dramatically strong interaction, and that means, of course, you can only excite the next Rydberg atom at a certain distance to the first one that you have in here. And what you would expect then within such a bubble of the radius given by the Blockade radius, where you can only excite 1 Rydberg atom, you don't know which of the ground state atoms you excited, so you would excite the atoms into this kind of W state, this entangled W state in the system. All right, so now we have this nice way of making any shaped initial states of our cloud, and now we can make a system where the Blockade radius is much larger than the initial size of our system. So we should only get really 1 excitation at maximum into the system. We can't squeeze in another excitation because the energy cost is just too large. So then we go and measure, and where do we find the Rydberg excitation? Well, we find it completely delocalized over the entire cloud. So it's like what you would expect. So if it's in this W state and you measure where that Rydberg atom is, it pops up here, 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 homogeneously over the size of your initial cloud. And that's exactly what we see in the problem, okay? Now, what can we say now? Can we say something about the entanglement we have in the systems in this W state? It's actually quite difficult because the entanglement is quite small. So in these W states, you have only 1 out of n atoms that is actually entangled. So there have been ways people have put forth to do this with Rydberg atoms, parity oscillations, state tomography that have worked really nicely. There's kind of a clever entanglement witness that had been proposed by Jakob Reichel's group that basically tries to measure the overlap of the state that you create with this initial kind of W state in the system, okay? And basically by measuring this overlap, you can show if it's below 0.37, you have no entanglement. If you have above 0.37, then you can say something about the number of entangled particles that are in the system. And there's few assumptions that go into this, like in all entanglement measurements, usually there are some assumptions that people either tell you or they don't. So the assumption here is that we really only have one Rydberg excitation in the system, but that's something we can measure, right? We can really check experimentally that there are never two Rydberg excitations in the system. We should have negligible motional decoherence. Well, we're starting in the mod state, everything in the ground state, so I think that's pretty well fulfilled. And we have from our laser phase fronts that are hitting the atoms, we have a symmetric coupling. So that requires a uniform laser phase that we shine onto the atoms. So we're not going under an angle onto the atoms, for example, onto the atomic plane. So all these three conditions are pretty well fulfilled.
Can I ask on that first one?
Yeah.
What if you have NE is equal to 0?
That's fine. You just are not allowed to have more than, that's fine. You're just not allowed to have two in there. That's fine with the entanglement witness criterion. So you should just not have more than one.
Well, you say post-selection, so you're post-selecting those out?
No, you're not, we're not, this is post-selection free. So we're not post-selecting anything. I'm just making sure that it's not, it's post-selection free. Yeah? There's no post-selection. That's important, of course. That's, for example, if you know Alex Kuzmich's experiment, where they showed kind of the square root n Rabi oscillations, that was post-selected. So that doesn't show you the full atomic dynamics. So here I'm talking about post-selection free, and we can check that we never have more than one Rydberg atom in the system.
If you have 0, there's no.
Well, but that's fine. That will go into the visibility of my Rabi oscillations. So this will be, so what I'm saying is then what you can use is the visibility of your Rabi oscillations. You turn on your laser, you get a number of Rydberg atoms, ground state Rydberg, ground state Rydberg. This visibility tells you something about the entanglement in the system. Okay, this visibility.
Post-selection free.
Yeah, sorry. It's my lack of English, my lack of English knowledge. Post-selection free, yeah. That's what I meant. That's important to clarify. So if we do that for our data, if we look at our Rabi oscillation data that I'll show you in a second, we can actually look at the visibility of our Rabi oscillations without correcting for any detection efficiency. These are the green points here. And these are the bounds of how many particles are entangled. If we correct for our independently measured detection efficiency of this single atom Rydberg detector, which I showed you before how it works, we get these red points. And if we believe that, then we have something like 100 particles entangled, which is about the size of the systems we're looking at. It just kind of confirms what we expect, that basically the whole system becomes entangled when we are in this kind of strong blockade regime. So here are these data that I wanted to show you. These are the initial clouds, the ground state atoms. This is where we find the Rydberg atoms averaged over many kind of experimental realizations. You always see we find them homogeneously distributed over the entire cloud size. Okay, so this one Rydberg atom pops up anywhere in the cloud. And you can see nicely how these Rabi oscillations speed up from the single particle Rabi oscillations when you just have one atom to the square root of n enhanced Rabi oscillations that you see here. And here again, there's nothing corrected, no correction for efficiency, detection efficiency. This is just the raw data I'm plotting here. Okay? And you can see it actually follows nicely pretty much this square root of n curve, although you see some deviations here, and I'll explain these deviations to you what happens for higher particle numbers. Now, for higher particle numbers, when the system gets larger and larger, we're not in such a good approximation anymore in the regime where the blockade radius is larger than the system size. So now you can squeeze in a second excitation. So where are you going to do it? Well, basically, because that's where the distance is largest, that's where you have the least interaction energy in the problem. So this could be here or here, right? So now we measure, and this is what we find. So we indeed find whenever we see two atoms, they're either on the diagonals here or on the diagonals here, okay? So what we believe we've excited is that we've excited the coherent superposition of the atoms here, Rydberg atoms here, and when we measure them, it collapses either onto this or this configuration, this spatial configuration. And just to show you beautiful pictures, if you do this with, with shorter and shorter, larger and larger systems, shorter and shorter blockade radiuses, you can get these beautiful Rydberg crystalline configurations where you have 6 Rydberg atoms, 7 Rydberg atoms, 8 Rydberg atoms, just self-organized into these kind of quasi-crystalline structures, just through their repulsive interaction energy, this very strong repulsive interaction energy. And we believe, again, that these are quantum crystals in the following sense, that actually there's nothing in the system that, when you measure the configuration like this, it could have occurred in a different rotational configuration, okay? And that's indeed what we see. If we average over many kind of single snapshots, you see all rotational configurations occur. It occurs symmetrically on the ring, and you have this blob in the center for this additional atom, Rydberg atom, which suggests, again, that you have the superposition state of all kind of rotational configurations. And that's why we believe one can speak of a quantum crystal, but of course, we should prove the quantum coherence. We have not proven the quantum coherence in these superposition states. When I'm just showing that all those rotationally equivalent states we are measuring, I haven't shown kind of the quantum coherence to you. And that's actually a difficult problem, an interesting problem, how to do that.
Now, I would have guessed that, at least for a sufficiently large system, that the crystals would show up, especially when you averaged, would show up in correlation rather than in actual position. Is it just that this isn't big enough for that to be the case? In other words, you might imagine that this hexagonal structure could itself be centered anywhere as well if the system was big enough.
Yeah,
and
but
what you've done is shown that it could be rotated anywhere, but it looks like it's always in the same position, or pretty much in the same position. Is that just because the borders are too close?
Yeah, I think it's the question, it's connected to that. I mean, the interaction energy cost, you just want to be as large a part as you can to be in the ground state. And we are trying to create the ground state of the system. Yeah. Of course, if you make the system larger, what you're saying is completely correct. Then this energy difference of something that is a little bit smaller than the maximum size gets smaller and smaller, and will be harder and harder to see the true ground state nature. And then you would have to go maybe to a correlation analysis to see that in these patterns. I mean, these just here, you can see it actually here. Look, this is the original size of our mod insulator, the gray curve, and you can see that the Rydbergs really appear at the boundary, at the border of the system. And yeah, that's, of course, it will get harder and harder to prepare that ground state the larger the system gets. Although I think with larger Rabi frequencies, we hope that we could make even larger crystals, maybe up to 10, 12 Rydberg atoms in the system.
Are those specific shapes consistent with the interaction? I mean, this is just
yeah, exactly. Yes, good question. I don't have the slide here with me. When you go from 6 to 7, it's exactly where you expect it to be more favorable to put the next atom in the center than rather putting it on the rim. That's exactly what you just by...
Can you raise the temperature and just melt it away?
Yeah, we try to do the low temperature, we try to get as close to the ground state as we can by actually sweeping the laser parameters in a way to create this icing, long-range interacting icing crystal in its ground state configuration. All right, so this is the Rydberg resonant Rydberg interactions. What I want to talk now is some recent experiments that we've been doing on Rydberg dressing. And the idea is basically that, if you have such a strong interaction, why not just take a little bit of it for the ultra-cold atom physics and, make these atoms, these Rydberg atoms, maybe a little bit more long-lived. And this is the whole idea of Rydberg dressing. And so the idea is now that you don't resonantly excite a Rydberg atom, but you detune your laser relative to this kind of pair energy here. And if you look at the interaction energy of two of these kind of dress state particles, I'll describe it in a second to you, you get this kind of soft core interaction potential where you can tune the height of the interaction potential. All right, so there's been a lot of motivation why you want to do this. Of course, super solids are one, tunable spin interactions, anisotropic tunable interactions, long-range interactions. So there's a lot of reasons why you want to do this. So let me explain you our approach of doing that briefly. So instead of the 2-photon transition, the first thing we changed to was to go to a single photon transition. Okay, that has a lot of advantages because, as you can see here, you can reach much larger Rabi frequencies. And in this game of Rydberg physics, the more Rabi frequency you have, the better. So the more powerful laser you can buy, the more powerful system you can do, the better your off, as you'll see in a second. Also, we're avoiding some kind of differential shifts here. So this is just, was painful to design, but yeah, I guess these wavelengths are not too unfamiliar, but for us this was a challenge. And then we get this nice kind of large coupling strengths. Here's just a beautiful picture of this resonator, one stage of the resonator making that 297 light. Okay, so now what happens if you shine this light onto your ground state atom excited to this Rydberg state with a single photon transition when you're detuned? Well, there are two things. Of course, there's you you form a dressed state now. Here you have this G tilde ground state atom, which is your original ground state atom plus a little bit of a mixture of the Rydberg state, okay? So you bought a little bit of Rydberg interactions, but okay, you've also paid something for that. That's the lifetime of your ground state, which will be contaminated by this Rydberg kind of interaction. Now, if you look at this, what's going to happen now, you have two things that are going to happen. You have, on the one hand, you have just the AC Stark shift that you're going to buy into when you shine in this laser of resonance. That's going to give you a huge energy shift. And on top of that, you're going to have, to second order or fourth order photon, 4-photon process, you're going to get this Rydberg dressed interaction. So this gives you this interaction, this soft core interaction potential that I was talking about. But look at the scales. This is really the Stark shift is much larger than this kind of Rydberg interaction scale that we're trying to resolve here. Okay, so now you've created these dressed state G tilde atoms. They have this kind of interaction potential here that we can see here, this soft core interaction potential. And we can tune very much about it. We can tune the height of this potential by the Rabi frequency of our laser, and you see that scales with the 4th power of the Rabi frequency. That's why I'm saying it really helps to have a powerful laser. So this height of the potential is in the kilohertz range for us, and is determined only by the laser Rabi frequency and the tuning. The range of the potential is determined by the C6 coefficient of the van der Waals interaction and the detuning of your system. And the lifetime, of course, that you have for your G tilde atoms, that's just going to be the lifetime of the Rydberg atom multiplied with the probability of being in the Rydberg state. And that's just given by 4 delta squared divided by omega squared. And this can be in the 10 to minus 4 range. So you have a longer lifetime than the Rydberg state, much longer lifetime, but of course weaker interactions now in these G tilde atoms. But that overall should make motional timescales accessible. Now this is theory, and then then comes reality. Okay, then so the theorist tells you, oh, you just have this beautiful 1 to the R6 curves, and then you do a full calculation, and this was done by Thomas Pohl in Dresden and his group, and you see you have this horrible molecular spaghetti of all these Rydberg curves, where here's the interparticle distance here, here's the energy scale, and everything I've been showing you were these beautiful curves out here, but reality is here. And these are dangerous distances for us. Look at this micrometer distances. This is exactly the lattice spacings that we have in our lattice. And what we found when we first did these experiments, we just turned on our laser, we found a very strange lifetime behavior. We found the following behavior, that the system rapidly decays, and then suddenly it becomes very long-lived. Okay? So very strange. You just turn on your laser, rapid decay, long-lived afterwards. And then we looked at the pictures, and they looked even more strange. So these are pictures of the atoms after turning on the Rydberg dressing. And sometimes we were just seeing complete lines of atoms missing. And we didn't do any addressing to that. That was just, happening to our atoms, so we didn't know what was going on. And what was going on here is the following, that at these short length scales, at, for example, square root of 2 lattice spacing, you're hitting these very sharp resonances. So your laser is detuned somewhere here red, and now you have these very steep curves, which create a resonance condition at specifically one separation in the lattice. And maybe that's square root of 2 of your original lattice spacing. And that's why when you're able to excite one atom, then they all fall in a line. So it's like a domino process. You suddenly have these resonant avalanches that can happen in the system. So I like to show this movie. It's exactly like that. You suddenly have one Rydberg excited, and that resonantly allows another Rydberg atom next by to be excited. And then they all fall in a line. Now, why that's exactly a line, I'm not so sure. I would have expected also it to go in that direction. Maybe that has to do something with our magnetic field configuration. Maybe you can also structure the whole thing to clear out in a checkerboard pattern or something, make as nice patterns as you do here. So I think that's actually very interesting. We didn't want to see that, but actually I think it's interesting short-range physics. So the upshot of that is what you have to be careful about is all these short-range resonances that can happen in the system. And it requires very careful atomic physics to look, what are states that are suitable to create kind of these dressed potentials. And one thing we found, for example, with Thomas was this 31p half state, P1 half state, where you can have a potential curve if you detune blue to that with your laser, and you only couple to this red curve, then there will be none of such resonances possible. Okay, so it just requires very careful atomic physics tailoring to achieve that. And when we did that, we were ready to go to measure these interaction potentials. So let me just finally show you that, this Rydberg dressing. So we have the two rubidium ground state spin states, F equal 2 and F equal 1. From this one, we do the Rydberg dressing. So this one acquires this long-range interaction potential as I've shown here, okay? And now if I look at the spin interaction that I get between those spins, I can write this in terms of this long-range interacting spin model. This is kind of the SZ describing my atoms either in the ground state here or in the excited state of my hyperfine state here. So if two atoms are in F equal 2, they interact through this kind of short-range interaction potential. If they're kind of in different spin states, they don't interact. Then there's the light shift that I talked about, the overall light shift. And then there's kind of a collective light shift. The ith atom kind of sees the sum of all the interaction potentials with the other atoms around it. Okay, so this is kind of the model from a theory point of view that we're realizing in the system. Yes?
So I haven't thought carefully, but if you have a p orbital, there's an antenna problem.
Yeah, you will. I'll come to that. I'll come to that. We'll see the anisotropy in the p orbital. We'll see in a second. Just wait. Hang on for a second. Okay. So the way to measure this now, all these different terms is through Ramsey interferometry that we all love so much. So you make a pi/2 pulse, bring your atoms into a superposition of the ground and the excited state, F state here. We let them evolve for a certain amount of time, turning on our dressing laser, so they evolve under the interaction of this Hamiltonian, and then we close this with a pi/2 pulse in the end. And then we blow away one spin component, so we're seeing kind of one spin component's position resolved in the system, okay? The distribution function. And we can see, as a function of this dressing time, we first of all see due to the Stark shift, we see these nice Ramsey fringes appearing in the system. And we see when you decrease the detuning that the Ramsey fringes, of course, get faster because you would expect this omega squared over delta, simple light shift scaling of the Rabi frequency. And if you look at this, you're almost made to believe that's fine, that's great, that's like omega squared over delta. That would be the green curve. But then you have students who are diligent and say, not good enough, we're missing something here in the description. And what we've been missing here in the description, why we can't get this to fit the omega squared over delta, is this collective interaction term, the shift that's introduced by the interaction with all the other Rydberg atoms, the mean field shift with all the other Rydberg atoms within the blockade radius of the system. And if you include that into the model, then you get kind of the red curve, and then you can see you get it to fit. So it's a tiny effect that you see, but it's really important. And you can also see dramatic consequences also of this. Sometimes you see shots like this one, where you see this collective shift in the core has introduced the same phase shift for all of those atoms in the core. That's why we see them all spin down. But at the boundary, because there are not enough atoms on the boundary, they don't have the same surrounding number of atoms, they get a different shift, a different phase shift, and they appear then, for example, as spin-up atoms in the problem. And then finally, you can do this, you can do a more detailed correlation analysis between the spins on these different lattice sites, I and J, correlate those spins. So you take pictures like the one I've shown you, you shift it by some distance and measure the correlation function of the spins in the z direction as a function of dressing time, and lo and behold, here you directly see this dressing potential showing up. So these spins getting correlated as a function of our dressing light being turned on. This is the 2D just spin correlation map that we have in the system. And this is what a cut through that looks like. And if you compare to a theory, this would be the red curve here. It matches beautifully with the theory corresponding to this short range kind of dress state interaction potential, the soft core interaction potential that I've been showing you. Just as a reference measurement, we do this without any spin resolution, and we see there are no correlations, of course, that we can see there. And then finally, we can come to what Carl has been mentioning. There's a p lobe, right? For p states, you can have the lobe pointing vertically to the plane, then you have isotropic interactions in the plane, or it can be tilted into the plane, and then you have anisotropic interactions. And we did that experiment also when it's tilted into the plane, and then you can see indeed these anisotropic interactions. This is what theory should tell us. This is what we see in the experiment. There's something to be said about this. Bimodal I talk with Steve about that. We can come back to this question. Actually, in order to see that, we need to post-select on only this data set here in the atom number. I can tell you details about why we had to do that actually in the experiment. It's connected to these avalanche processes that we see before. Okay, so this is all I wanted to tell you about the Rydberg dressing, showing you the pictures that we can directly see these Rydberg dressing potentials. We can realize this Rydberg dressing. We're looking now into how we can extend the lifetimes of this to engineer kind of spin models with long-range interactions in these systems, and maybe extend this even to look for supersolids, for example, in long-range kind of motional timescales that we can have in the system. All right, so the team on this experiment is around Christian Groß, and the main student on this was now Johannes Zeyer and Peter Schaus. Peter is now in Princeton with Wasim Bakar, And Johannes is taking fantastically over and doing all the work on the Rydberg dressing is due to his work. And we had a nice theory collaboration. You know, I think in this game with Rydberg physics, you're lost without atomic physicists. And Thomas Pohl and Tommaso Macri and Rick van Bienen have been a tremendous help in trying to understand which potentials we should use in the experiment. All right, I think I've taken too much of my time already, so I'll leave you with this picture.